Okay, section 1.6, scatter plots and lines of best fit. There's a possibility that you've never seen scatter plots before. A possibility you have. I might have done it in 7th and 8th grade math. It says not always will real life data lie in a perfect line. The problems that we've had in the past few days, we've had perfectly straight dots. You just connect the dots, it was a perfect line. Real life, guys, that doesn't happen. And to me, and I tell my Algebra 2 kids this, to me I can see to where what I'm about to show you, and you're only getting the bare minimum. You're just getting an introduction to scatter plots. Algebra 2 and pre-calculus, we go really in depth in it. And if you ever want to, there is a video on the pre-calculus. We've already done this in pre-calculus. There's a video on the pre-calculus site. I think it's section 1.4. That if you ever want to watch it, you can see a more in-depth view of what we're about to do. But what scatterplots does is in real-life situations, you can take and you can analyze data. And once you analyze the data, you can see some of the graphs I have here. That's more of what your graphs are going to look like. And this kind of answers the question that you had a while ago also, is how does the graph benefit us? Well, we're conducting a test. And we're testing, let's see, what's some of the examples I have down here? Let me look. We're conducting a test, and we want to know age and height. We want to know, the older you get, does that have any impact on how tall that you are? You know it's going to. You know that it's going to. The older you get, the taller you get. But here's the thing about it, just because you're 16 years old does not mean that you're going to be 5'10". Does that make sense? You might be 5'10", you might be 5'11", you might have an outlier down here that's 4'3". But your data is going to look somewhat like what we have here. You're going to have a scatter plot. What you can do is you can use scatter plots to make predictions, and that's the biggest thing. That's how we're going to use it. You can use scatter plots to make predictions of, okay, what about a 2-year-old child? We want to know about how tall are 2-year-old children. So we can take and we can do a line of best fit, and we'll talk about all that in just a second, and kind of predict how tall 2-year-old kids are. Will it be exact? No. No, it's a prediction, but it should be pretty close. It says not always will real-life data lie in a perfect line. However, many times the data, even though not perfect, will closely follow a pattern. We may see a trend in the data. An effective way to look at these trends is by using scatter plots. A scatter plot is simply a cluster of points. Sometimes the cluster will closely resemble a line. If there seems to be a relationship such as a line, we say that we have a correlation. You've heard that word correlation before. It means there's a relationship there. There are two types of correlations that resemble lines. We have positive correlations, which all these on the left-hand side are positive correlations, and you have negative correlations. The ones on the right-hand side, most of those are negative correlations. And when I say the right and left-hand side, just those first few. Positive correlations, easy to remember. Positive correlations slant up. Negative correlations slant down. If you can remember what I just told you, this will be a really easy lesson. Positive, up. Negative, down. And when I say slant up and slant down, we're moving from left to right, just like you're reading a page. From left to right, we're going uphill. From left to right, we're going downhill. Positive correlation and negative correlation. Now let's talk about some things that do have positive and negative correlations. Well, before we do that, let's talk about strong and weak. Does it make sense why this is a strong positive? Do you see that if we drew a line through that, all of those points are really close to that line? That's it. They're sticking together. They're strong. Okay? The stronger they are, the tighter they are. Here, it's a little bit weaker. That you're exactly right. That's a good way to think of it. You don't touch near as many dots when you pass a line through it. Strong negative. Hit nearly every with a line. A moderate negative. Moderate, the word moderate is kind of like medium. It's in the middle. And then we have a weak one down here. Look at this other graph we have. And these are just examples of different types of scatter plots. Is that a positive or a negative, the one that I circled? It's neither. You just got points everywhere. You can't tell if they're slanting uphill. You can't tell if they're slanting downhill. Which this weak negative, it's not too great. But the none, you don't even know where to start with a line. There's just points everywhere. So that would be actually no correlation. So now that we've seen these different types of graphs, let's talk about different things that have correlations. In a positive correlation, since you're going uphill, as the x increases, as you travel to the right, you also travel up. As x increases, y also increases. A negative correlation, as you go to the right, let me scroll back up. A negative correlation, as you travel to the right, your graph goes down. So as x increases, y decreases. Let's talk about some things with positive and negative correlations. Positive correlations, age and height. I've already told you about that. As your age increases, most of the time, your height increases. Wake him up for me, please. Education and income. This is a good one. The better education you have, most of the time, the more money you make. That's what I'm saying here. As your education increases, your income increases. Hours of working out and strength. The more you work out, the stronger you get. You see that as one of them increases, the other one also increases. Negative correlations means as the first one increases, the second one decreases. Hours spent on sports and hours of free time. If you're training 10 hours a day, more than likely you're not going to have a lot of free time. So as the hours you spend in sports increases, the amount of free time you have decreases. Makes sense. That's a negative correlation. Days of running and minutes it takes to run a mile. If you run a mile for 50 days, then the time it's going to take you to finish that mile starts going down. Makes sense. As the days increase, your time decreases. You get more in shape. And the final one for a negative correlation, hours of sleep and the number of times your head nods in class. Right? If you get more hours of sleep the night before, the less likely that you're going to nod off in class. So the more hours of sleep that you get, as hours of sleep increases, nods decrease. No correlations. And there's a ton of things we could list for no correlations. Age and eye color. Do they have anything to do with each other? No, there is no correlation there. Money you possess and the number of siblings you have. No. Well, I could kind of see in a way that those would have something to do with each other, but we're going to say not really. If you're a millionaire, I'm sure you could do a study and take all the millionaires, and they're not all going to have 3 brothers and sisters. There's not going to be a relationship there. The one, and I believe only example that we've got here. If we have a correlation, then we should be able to closely fit a straight line through the points. This line is called the line of best fit. Why would we call it the line of best fit? Because it fits best. Makes sense. Most of the time in math, we don't call it stuff that's just completely off the wall. We use something that's pretty applicable. So a line of best fit is the line that best fits the points. This line can also be used to make predictions about the data. Example 1. It says make a scatter plot. Make a scatter plot for the data below on the number of people working on farms in various years. Then draw a line of best fit. Describe the correlation as strong positive, strong negative, or little to none. No correlation. So again, what we've got here, we got different years, and the number of farmers, farm workers in thousands, pretty much the number of people that work on a farm. In 1940, you had nearly 9,000. 1950, you had nearly 7,000. 1960, 4,000. 1970, 3,000. 1980, about the same. 1990, about the same as well. Before I even graph it, can you tell me what type of correlation it's going to be? You don't think it would be? Negative. As the years increase, as you go through the years, what happens to the number of farmers? They decrease. They start going down. That'd be a negative correlation. As X increases, and our X's here would be our years, the Y's decrease. They go down. So let's try to graph this. Yeah, that's a lot of other things. People started getting interested in other things instead of farming. So 1940, 1950, 1960, 1970, 1980, 1990. Let me show you a trick a lot of times we use for years. The Algebra 2 book, we do this nearly every problem. Instead of starting, because we've got to graph this, instead of starting at 1940 being, well, we're going to have to somehow change our scale. Let me show you what we'll do a lot of times. We'll let this be, let me go back to my notes. We'll let this, 1940, be year 0. And we're going to have to say somewhere on our graph, x equals 0 is 1940. So, can you tell me what 1950 would be now? Close. So therefore, again, if x equals 0 is going to be our year 1940. 1950, think about how many years later that's going to be. That's going to be x equals 10. Good job. So let's go back to our chart. If 1940 is x equals 0, 1950 will be x equals 10, 1960 will be 20, 1970 will be 30, 40, and 50. The reason we do that, what about 1943? What did 1943 be? 3. What did 1945 be? 5. Does that make sense? So we'll, instead of having to graph 1940 to 1990, a lot of times we'll let it be x equals 0 to 50. So let's say in our scale here, we got 9,000, 7,000, 4,000, 3,000. I've got to somehow fit this on here. What are we going to let each tick mark count on our y-axis to fit all those? 1,000 is a good number, because about how many tick marks are we going to use? Actually 9, because we got 89.95, which is right at 9,000. So we'd only use 9 tick marks, so that'll work. We're going to let our x-axis, I'm going to say every tick mark counts 5, just so we can spread it out a little bit. 5, 10, 15, 20, 30, 40, 50, 60, that's plenty, isn't it? We only went up to year 50. Yeah, to where it spreads it out more. And then we're going to let each tick mark up count 10,000. And if you want to, if you want to spread out even more, because the more spread out that you're able to get it, the better it's going to look. You could let each one count 5,000 if you wanted to, but we said 10,000, right? So our first one's going to be 10,000, and I'm just going to put a 10 there. We'll know that it's in thousands. 10, 20, 30, 40, 50, 60, 70, 80, 90,000, and I'm going to write there in thousands, just so we can remember. So at year 0, we have right at, I did tens, didn't I? It's supposed to be 1, 3, 5, 7, and 9. My bad. 1, 3, 5, 7, and 9,000. So year 0, we have nearly 9,000 farmers. Can we get this point exact? No. No. Because, I mean, 8,995, we can get it really close. We're not ever going to get that exact. So it's right there nearly at 9. Nearly 9,000 farmers. That's at year 0. Year 10. We had nearly how many? So year 10, we go over to 10, and we're going to go up nearly to 7. So right below 7. Does that make sense to everybody? It's not going to be linear, you're exactly right, but it looks similar to being linear. 1960, we have a little over how many? Have a little over 4,000, so we go up a little bit past 4. Again, we can't get it exact. Get it as best you can. Get it as close to that as you can. 1970 or 30, we have a little under. So 30, a little under 3. 40, a little under 3 as well, a little bit less under 3. And 50, a little bit higher actually than that previous one. So line of best fit, let's talk about that now. We've got our points plotted. Now we've got to try to figure out what line best fits this. This is where it separates Algebra 1 from what you're going to do in Algebra 2 and pre-calculus. Algebra 1, we just guess. Algebra 1, we just draw a line that we think best fits it. I'm going to say about through there. Just as close to those points as you can get. Is it going to be an exact answer? No. No, just get as close as you can get to all the points. Algebra 2 and pre-calculus, we use our calculators and we actually find out what is the line of best fit. Using what's called residuals, how close are the points to the line. We're trying to minimize the distance between the points in the line. Algebra 1, we guess. So the question says, let's go back and finish the last one. It says, use the line of best fit to predict the number of farmers in the year 2000. If 1940 is 0, 1950 is 10, what's going to be the year 2000? 1940 was 0. 2000 will be 60 years later. So we look at our graph and we're trying to predict, okay, for 1960, and let's come out here to 60, or not 1960, excuse me, 60 years later, the year 2000. So come out here to 60 and go up to your line. We're using it to predict, and let's see, let's go over to where it's at. Is it a little bit over 3? It's a little bit over the first tick mark. Do you see that? 60 years later, go up and then go over and read it. It's in between 1 and 2. Make me a prediction there. A little bit over 1,000, right? It's a little bit above the 1. So I'm going to say 1,200. But again, we're not looking at points. That is a good observation. We're not looking at points though. We're forgetting all about the points. This is our predictor line. Once we have our line of best fit, we use that line to predict it. You're getting into a little bit more advanced, which I'm glad you made that observation, because honestly, a line doesn't fit that very well. The best graph, and is there a such thing? These are another name for these lines of best fit, are linear regressions. You also have exponential regressions, polynomial regressions. You have different types of graphs, and we talk about that more in Algebra 2, that could probably fit this better. Honestly, with this data set, you could probably fit an exponential graph to that better than you could a linear. You could fit a curve better than a line, and then that would be much, much, much more accurate. But the way we're going to do it today, you fit a line as close as you can to it. For 60th year, you go up and you use that line to make a prediction about how many farmers there's going to be. So any questions?